Well, let us continue with our discussion on steam table. So, more or less we have discussed most of the important features of steam table. Now, I just like to give one example, how does it look, what are the values we get. So, it is like this. So, steam table, temperature based, so we will have the columns like this T, P, Vf, Vg and Vfg. We will have Hf, Hg, Hfg, Sf and Sg. Now, due to shortage of space, I will not write down the units here. So, let us take the example at a temperature, steam properties at a temperature of 100 degree Celsius. So, if we refer the steam table, we have to go for temperature value at 100. Once we specify this, other values can be directly read from the steam table. Like pressure, we will find it is in kilopascal and the value we will see this is 1.0135. This is the pressure value. We know at 100 degree Celsius the water boils at under atmospheric pressure. So, basically this is the atmospheric pressure. Corresponding specific volume of saturated liquid will be 1.044 meter cube per kg. Corresponding specific volume of steam, that will be 1.6729. Vfg, of course, one can calculate, I am not giving the value. Hf, that is the enthalpy of the saturated liquid at 100 degree Celsius, that means at atmospheric pressure, it will be 419.04, that is kilojoule per kg. Hg, this will be 2257.0 kilojoule per kg. Sorry, this is wrong. This will be 2676.1 kilojoule per kg, and Hfg, that will be 2257.0 kilojoule per kg. Sf will be 1.3069 kilojoule per kg Kelvin, and Sg will be 7.3549. So, these are the values we will get. That means, at atmospheric pressure or at a temperature of 100 degree Celsius, the latent heat of evaporation or condensation, that is 2257.0 kilojoule per kg. For the evaporation of 1 kg of water at 100 degree Celsius to 1 kg of vapor at 100 degree Celsius, we will need this much amount of thermal energy. Now, if we see the steam table, we will see that this Hfg values, that will go on decreasing with temperature. As we will go for higher temperature or higher values of pressure, we will see this value of HFG that will go on decreasing, and it will diminish at the critical point. As I have told earlier that at the critical point there is no demarcation between the liquid phase and the vapor phase, we will see that gradually the latent heat or the difference of enthalpy between the saturated liquid state and the saturated vapor state, that will go diminishing and it will vanish at the critical point. That is what we will find. The same thing happens in case of the specific volume. The specific volume, the difference between the specific volume will be higher at low pressure and low temperature, but as we go towards the critical point, this difference will go on diminishing and it will vanish at the critical point. So, this is for the first part of the steam table, where we have got property data for the saturated state of the fluid, where we have got data for saturated liquid and saturated vapor. Now, in this steam table we have got three parts, as I have mentioned number of times. This part is liquid, this part is a mixture of liquid plus vapor, this part is vapor or superheated vapor. So, this liquid part is known as, either it is called subcooled liquid or decompressed liquid, compressed liquid or subcooled liquid. Why it is called subcooled liquid? Because, let us take this part in details and then explain. Let us take the help of a TS diagram. This is the TS diagram, and here we are having a constant pressure line like this. P is constant. We are interested in determining the property of a liquid whose state is given by of a liquid sample at P star T star. So, we are interested in that. So, this is actually P star pressure and T star temperature. So, let us say through P star T star, if I pass a constant pressure line, this will be something like this, and a constant temperature line is something like this. So, this is your T star. All right. So, this is your P star line and this is your T star line. For P star, we are having the saturation temperature at, let us say, T dashed. For corresponding to P star, the saturation temperature is at T dashed. So, what is the relationship between T star and T dashed? What is the relationship between T star and T dashed? T dashed is definitely higher compared to T star. So, that is why this state is subcooled state. Corresponding to the temperature is corresponding to the pressure, the temperature is below the saturation temperature. So, this is in subcooled state. So, that is why we call the liquid state as subcooled state or subcooled liquid. Then if I take T star, we can send through T star a constant pressure line, and the constant pressure line will be something like this. Let us call this constant pressure line or constant pressure as P1. So, what is the relationship between P1 and P star? P star is greater than P1. So, if we take this temperature, corresponding to the temperature, the saturation pressure is P1, but the pressure of the liquid is more than the saturation pressure. So, that is why this liquid is also called compressed liquid. So, the liquid state is denoted either as subcooled liquid state or compressed liquid state. In general, okay, let me take property at subcooled liquid state that will be a function of pressure and temperature. In general, this is true, as I have discussed earlier, that for a pure substance, if it is in a single phase condition, then the property will be dependent on two independent thermodynamic properties. Two independent thermodynamic properties which are easy to measure, let us say, are pressure and temperature. So, any property of the subcooled liquid state that can be expressed as a function of pressure and temperature. But what has been seen that the liquid property or property of the subcooled liquid, that is a weak function of pressure, whereas it varies with temperature. So, for determining the property of the subcooled liquid, what do we do? This T star and P star, though these two independent conditions or state of this sample is given, we determine the property at the saturated state corresponding to T star. We do not bother what is its pressure. If we know the temperature, then the saturated liquid property corresponding to that temperature we take as the property of the subcooled liquid. So, that is how the liquid property is determined, or the property of the subcooled liquid state is determined. So, here the temperature is the only constant, the temperature we take, and corresponding to that saturation temperature we determine the property. And there, of course, we have our steam table. Here the properties are given for saturated liquid condition. So, we can determine the property using the table very easily. So, property of the subcooled liquid state I have described how we can determine. Then we go for property of liquid and vapor. Here also I have already described how using the saturated properties and the dryness fraction, the property at any point in this two phase region or in the mixture region can be determined. So, here also we do not have any difficulty. Then we go to the other side of the dome, on the right hand side of the dome, which is the superheated vapor region. In the superheated vapor region, so property of superheated vapor. So, again here the property will be function of two independent thermodynamic properties. And as I have mentioned again, earlier also, that is pressure and temperature are two independent properties which can be measured easily, which based on which other properties can be expressed. So, this is a function of pressure and temperature. Here of course, we cannot make any compromise. So, property of the superheated vapor, it depends both on pressure and temperature. All right. In the second part of the steam table, we have property of superheated vapor or superheated steam. So, second part of steam table, property of superheated steam. This will give you property of superheated steam. Again, they are functions of pressure and temperature, and it is generally tabulated in this form. Let us say it is, let us take a particular value. Let us say the pressure value is given, that means we have tabulation of steam properties at this 0.10 megapascal. So, pressure is equal to this value. This gives saturation temperature temperature 45.81 degrees Celsius. All right. So, we can have tabulation of the property of superheated steam for a pressure of 0.1 megapascal and which corresponds to saturation temperature of 45.81 degrees Celsius. So, the table looks like this. We will have values at different temperatures. Then what values we will have? What property values we will have? We will have specific volume, we will have enthalpy, we will have entropy. So, this is in degree Celsius, this is in meter cube per kg, this is kilojoule per kg, this is kilojoule per kg Kelvin. All right. So, first we will have, this is saturation temperature, we will have 14.674, then 2584.7, 8.1502. Actually, this is the property of saturated vapor. Then we can have at 50 degrees Celsius. So, saturation temperature is 45.81 degrees Celsius, 50 degrees Celsius means it is superheated. Then it is 14.869, 2592.6 and 8.1749. Similarly, one can have values at 100, at 150 and so on. So, this is how the superheated, property table for superheated steam look like. And obviously, either in the first part of the steam table where properties of saturated liquid or saturated fluid is tabulated, and in the second part of the steam table where the properties of superheated vapor is tabulated, there at some regular interval the property values are given. So, that means in between, for in between parameter values, if we have to determine the property, we have to go for interpolation and we go for linear interpolation. This will be clear when we will solve some problem, and probably sometimes we have to go for double linear interpolation, means linear interpolation we have to do for two different parameters. So, that is what we will learn when we will solve some problem. So, this is all regarding the description of steam table, and the steam tables are available in, by different publishers. So, we can get any one of them which is in SI system and use them for solving the problem. The purpose what is served by this steam table, almost the same type of calculation one can do using a Mollier diagram or HS diagram. Only thing is that in HS diagram sometimes we have to read in between the graduation. So, we have to take some sort of I estimation, and that may induce some sort of an error. Okay. And of course, we have to draw some diagram, and from that diagram we have to read the readings, we have to take the readings. So, some sort of error may creep in due to the geometrical construction, due to I estimation, etc. But in general those errors are negligibly small. If somebody is careful, then those errors are small. In general, one can use either a steam table or a Mollier diagram. But it is always advisable, if you are using a Mollier diagram, then you sketch the process whatever you are using for calculating the property values on the Mollier diagram, you have to give the sketch also in the answer scripts or in your verbal description of the process. That sketch has to be written description of the process, you have to give that sketch, that is mandatory. Now, so far so regarding the steam table and calculations regarding the steam table. If we go again, if we see the property of pure substance, and any diagram, any standard thermodynamic diagram, if we consider like the TS diagram, let us say the TS diagram, we have got the critical point here. This is C or critical point. This is a constant pressure curve. Through the critical point, you will have a curve like this. Beyond the critical point, you will have curve like this. All right. Now, if the state of the fluid is such that it is somewhere above the critical point, then we consider it to be a gas. And in our engineering thermodynamics, we will get lot of example, or in day to day engineering practice, we will get lot of example where a gas is the working substance for the equipment or for the engineering cycle which we are operating. So, we should have some idea regarding the properties of gas and different processes involving gas as the working medium. Now, though the behavior of gas that can be different at different ranges of pressure and temperature, there is some sort of idealization. Ideal gas. So, when we talk of ideal gas, we have some sort of idealization. Of course, from physics point of view or from molecular point of view, there are certain assumptions by which this idealization can be made, but I will not go into those. But the macroscopic behavior which describes the ideal gas, that behavior we are familiar with, and that is given by a very well known law like this. For ideal gas, we can write PV is equal to nRT. So, this is the ideal gas law. Though one may argue that no gas is ideal, because if we go through the assumptions which are made for ideal gas, we will see that they do not hold good for any of the gases, but we will see that there are ranges of pressure and temperature where lot many gases behave like ideal gas. So, we use this law and we analyze different engineering processes. This is known as law for ideal gas. And what are the different symbols here? P is the pressure, V volume, N number of molecules, then R bar, that is universal gas constant, T absolute temperature. So, these are the symbols: pressure, volume, number of molecules, then universal gas constant and absolute temperature. So, basically it denotes a system, a closed system, something like this. Piston cylinder arrangement. It can be some other arrangement also, but basically it is a closed system where the mass of the gas remains constant, and then the volume, pressure and temperature, they can vary, and we have got methods for measuring them. So, if we can measure them, then for any particular measurement, pressure, volume and temperature will follow. This is the gas whose mass remains constant, piston movement is possible, and then we can measure the pressure, volume and temperature. So, at any instant the pressure, volume and temperature, that will follow this type of a relationship, and this is valid for any ideal gas. The universal gas constant R or R bar, whatever I have written, its value is 8.3143 kilojoule per kg mole Kelvin. This is the value of the universal gas constant. Then the law which I have written, that is PV is equal to nRT, sorry, nRT or nR bar T. This can be rewritten in this form: PV is equal to mRT, where n I have replaced by this formula m by mu. M is the mass of the sample of gas, the gas which is confined in this piston cylinder arrangement. M is the mass of that sample of gas, and mu is the molecular weight of the gas sample. R is characteristic gas constant. This is the characteristic gas constant. So, what we have got, let me write down once again. Different relationships: PV is equal to nRT, or in other words we can write PV is equal to mRT, where n is equal to m by mu. Then in the next step what we can do, m we can bring on the left hand side. So, PV by m is equal to RT, or PV is equal to RT. So, this is your specific volume. So, these are the different forms of ideal gas law. Sometimes this is also called combined Boyle's and Charles law, as we know from our elementary physics. So, this law we will use for determining different properties and determining work done, heat transfer, etc. using thermodynamic laws. So, basically if we want to do thermodynamic analysis of reversible processes, thermodynamic analysis of reversible processes with compressible fluid so which is nothing but a gas as the working medium. So, basically we want to do this thing now, thermodynamic analysis of reversible processes with compressible fluid or gas as the working medium. So, we can start, or we can take the example of different processes and then we can analyze. But in this analysis we will use what we will use? We will use first law, law of thermodynamics, So, that is we will use dq is equal to du plus dw. Second, we will use relationship for entropy. What is that? dq by t reversible is equal to ds. This we will use. Third, relationships for specific heats. This also we will use, and these relationships are these relationships are how can we express the relationship of specific heat? dq, let us say this dq is equal to Cp, first let us say Cv delta T for constant volume process. So, this we can write volume is equal to constant, and this also is equal to du internal energy. Then we can have dq pressure is equal to constant is equal to Cp dt is equal to dH. This also we will use. Then
DH also we can write, sir.
dH I have written.
That is U plus P, PVP.
That we will see. Then fourth, what we will use, equation of state, what we have discussed just now, that is PV is equal to RT. So, these are the relationships which we will use for determining or for the thermodynamic analysis of reversible processes with compressible fluid, that is a gas, as the working substance. So, let us start with some simple process and see how we can proceed. So, first let us take a constant volume process. Constant volume process. So, in a constant volume process, we will get let us try to plot it on a PV diagram. This is a PV diagram. So, constant volume process, volume will remain constant. So, either one can have this to be the initial point and this to be the final point, or reverse. That means either the process can go from 2 to 1 or 1 to 2. So, this is a constant volume process. Now, if it is a constant volume process, first let us try to apply the equation of state. So, one can write P1 V1 P1 V1 is equal to RT1 and again P2 V2 is equal to RT2. So, this is valid for any thermodynamic process. This we have not written for a constant volume process or constant pressure process, but this is valid for any two end states 1 and 2. We can write these relationships. And if it is a constant volume process, then we can get V1 is equal to V2. So, if V1 is equal to V2, so for this is constant volume process, then we get P1 by P2 is equal to T1 by T2. So, this is the property relationships for a constant volume process. P1 by P2 is equal to T1 by T2. Then next we go for what is the work done, W1 to 2 in a constant volume process. So, W1 to 2 is equal to 1 for a compressible fluid 1 to 2 PdV. This is the PdV work that gives you the work done during the process, and as dV is equal to 0, change in volume that is equal to 0. So, we will have W1 to 2 is equal to 0. So, this comes from this diagram also. If it is a constant volume process, then area under the curve is 0. So, work done during this process, that will also be equal to 0. Work done during a constant volume process for a fixed mass system, that is equal to 0. Then what is Q1 to 2? What is the heat transfer during this process? Heat transfer during this process, of course, we can apply first law of thermodynamics is equal to U2 minus U1 plus W1 to 2. This is equal to 0, and in this case this will be CV T2 minus T1. So, that is how we will get the heat transfer during this process. This is again equal to the change in internal energy. Then what is the change of entropy during this process? Change of entropy will be S2 minus S1, that is equal to dq by T, that is equal to 1 to 2 Cv dt by T, and then we can write Cv dt by T 1 to 2. So, S2 minus S1 is equal to Cv ln T2 by T1. So, you see, we have started with a constant volume process, which is one of the basic process, simplest process involving a compressible fluid. We can determine the property relationships, and then we can determine the work done, the heat transfer and change in entropy. Similarly, we can proceed with other processes. Second process let us take as a constant pressure process. Well, before doing that, if we know this is the change in entropy S2 minus S1, how can we plot the process on a TS plane? So, this is your T and this is your S, TS plane. So, on TS plane, how do we plot this? How will this process look on the TS plane? It is some sort of logarithmic or exponential relationship. So, we will have something like this 1 to 2, this is 1, this is 2. So, we will have a process like this. Either we can have a cooling process or a heating process, something like this. So, next process which we can think of is a constant pressure process. In constant pressure process, again it is easier to visualize in a PV plane. So, we will have P1 is equal to P2. So, if P1 is equal to P2, then from equation of state we can get a relationship between V and T. So, basically it is P1 V1 by T1 is equal to P2 V2 by T2, and P1 and P2 they are equal. So, we can get V1 by V2 is equal to T1 by T2. So, this is the property relationship for a constant pressure process. Then next we can determine the work done. W1 to 2, that is equal to integration 1 to 2 P dV. Here P remains constant, actually P1 is equal to P2 is equal to P at any point during the process. So, one can take this P outside the integration sign and 1 to 2 dV. So, this will become P V2 minus V1, and obviously as we have discussed earlier. So, this work done will be given by the rectangular area under the constant pressure curve. So, this is how we will get the work done during the constant pressure process. What is the heat transfer? Q1 to 2, that is equal to U2 minus U1 plus W1 to 2, and this is equal to Cv to T2 minus T1 plus P V2 minus V1. Then one can write it like this, sorry, Cv T2 minus T1 plus P2 V2 minus T1 V1. Then one can express it like this. Cv T2 minus T1 plus what is P2 V2? P2 V2 is equal to RT2 minus RT1, and this is Cv T2 minus T1 plus R T2 minus T1. So, this is Cv plus R T2 minus T1. So, this quantity is nothing but Cp. So, basically it is Cp T2 minus T1, or one can write it in terms of enthalpy. This is H2 minus H1. So, heat transfer during the constant pressure process we can determine by either of this formula. Either it is Cp T2 minus T1, or this is nothing but the change in enthalpy, that is H2 minus H1. So, I think I will stop here, and next day we will see what is the change in entropy.